Alright, so welcome to the last lecture of the semester. So today we're going to continue talking about heat exchangers. In this case, we're going to talk about the double pipe heat exchanger. So for this, we basically have two tubes. They're concentric. So we have an inner tube here, and then we have an outer tube. On the inner tube, we're going to have hot fluid, and then in this annulus here, we're going to have cold fluid. And for this experiment, we're going to have parallel flow and then counterflow. And we'll talk about this later on in the actual lecture. And then here we have our setup, our test setup. So let me zoom in. So all of these circles here, they're the thermocouples that we have. So thermocouples 1 through 9, they're going to be in the inner tube and they're going to measure the hot fluid. Let me make sure I remember that correctly. Yep. And then the thermocouples 11 through 18, they're going to measure the cold fluid, and they're going to be in the annulus. And as you can tell, all of these thermocouples, they're at the same axial location, so we can measure both of them, at the same spot. Okay, and then in the lab, what we would have done, of course, we can't do it, we would have two kind of setups where we have uninsulated and then insulated for the heat exchanger. So basically, we would just have some gray foam, basically. Gray insulation. Okay, so what we do is we would start out with the uninsulated parallel flow. And for the hot water, we would keep that at 10 gallons per hour, and then for the cold water we would start that at 2.5 gallons per hour, and then we would increase that up to 10 gallons per hour in increments of 2.5 gallons per hour. So if we go to our spreadsheet here, this is what you would have had in the lab to fill out. You see that we have uninsulated here and here, and then insulated there and insulated here. Then we have our thermocouple, so 1 through 9, that's for the hot water, and then 11 through 19, that is for the cold water. Actually, 19, I think that's for the static port. Thermocouples 11 through 19, that's for the cold water. Okay. Alright, so so we're doing that, and then we have the insulated versions down here. Okay, so let's go back to the document here. So we have the uninsulated parallel flow, and then we have the uninsulated counterflow, and then we have insulated parallel flow, and then insulated counterflow. And we're basically doing the same thing each time where we're only going to adjust the cold water flow rate. Alright, so for the data reduction, what you have to do is measure or graph the temperature versus the axial position. And we're going to do that for all of the different flow rates, and we're going to do that for our insulated configuration and our uninsulated configuration. And then for each of those graphs, you're going to have two curves on there. So you can have one curve for the cold fluid, and then one curve for the hot fluid. Okay, so number 1 and number 2, they basically say the same thing. This one should just say insulated right here. Okay, so number 3, for the uninsulated trials, you want to calculate the heat loss, basically, and then we're going to plot that against the flow rate. Sorry, I'm looking at my notes here. Okay, and then for the last one, we're going to calculate the heat transfer coefficient U, and then we're going to plot that against the flow rate as well. And that's the flow rate for the cold fluid. Okay, and then for these last two graphs for number 3 and number 4, we're going to have two curves again, where one curve is for the parallel flow, and then one curve is for the counterflow. Okay, And then, as always, this last part, this error analysis, this is differential error analysis, or it's math-based, basically. I still want qualitative error analysis, so I want you to talk about, some possible sources of error. I know that's harder to do now because you weren't actually doing the experiment in person, but you should still have some stuff. Alright, so with that, we're going to go ahead and get started on the lecture. I will remember. Okay, so what I've written out here is just recall that a heat exchanger is a device that's used to transfer heat between two fluids that are at different temperatures and are separated by a solid wall. So in our case, we have two walls, but what we have is an inner tube that is at a hot temperature, and then in the annulus we're going to have a cold fluid. So those two different temperatures are those two different water flows. They're at two different temperatures and they're separated by a solid wall. And then the goal we have is to raise or to lower the temperature of these fluid streams. So now we're going to talk about the geometry of the double pipe heat exchanger. Okay, so the double pipe heat exchanger, again, that's going to be composed of two concentric tubes. So I have tube 1 and I have tube 2. And then in the inner pipe we have hot fluid, and in the annulus we have cold fluid. In this case, it's going to be water. Don't let your life pass you by, and weep not for the memory. Okay, so for this experiment, again, we're going to have two different configurations. We're going to have parallel flow and counterflow. So as you can tell from my beautiful drawings, we have parallel flow on the left, where the flow for the hot fluid and the cold fluid, they're going to be going in the same direction. And then on the right we have counterflow, where the fluid flow is going in the opposite direction. Remember all the good times that we had. Okay, and then in contrast to a cross-flow heat exchanger, the temperature of the fluid is going to be a function of the x location. So we're going to see this right now when we compare the parallel flow and the counterflow. I let them slip away from us when things got bad. How clear. Okay, so what I have here is a figure for the temperature distribution for parallel flow. So you probably recognize this figure from your heat transfer textbook. I think you're taking that right now, and you probably just covered heat exchangers. I don't know. I think that's kind of late in the course. Okay, so anyways, what we have is both fluids, they're going to enter at the same position, and they're going to, again, flow in the same direction. So what we have here is the hot fluid. This is going to, enter right here, so to say. And then the cold fluid, that's going to enter right there, where we have TH, I, that's going to be the inlet for the hot fluid, and then TC, I, that's going to be the inlet for the cold fluid. And then what we see here is we have a really big temperature differential. So at the inlet, the hot fluid, this is going to be really hot, so it's way up here for the temperature. And the cold fluid, that's going to be, it's going to be cold. So it's down there. But as we move along in our heat exchanger, the hot fluid is going to transfer some of its heat to the cold fluid. So the hot fluid is going to become not quite as hot, and the cold fluid is going to heat up. So we get this, this kind of curve here for each temperature for each fluid. So this temperature differential, as you can see in the figure, it's going to decay as we increase our x position. However, although it's decreasing for that temperature differential, the cold fluid can never exceed the temperature of the hot fluid. So, although this cold fluid has increased in its temperature quite a lot towards the end, it's never going to have this kind of appearance where the cold fluid is going to be higher than that of the hot fluid. So it's not going to have an appearance like that. It's never going to cross over.
Clearly I first saw you smiling in the sun. Wanna feel your warmth upon me. I wanna be the one. I will remember you. Will you?
Okay, so now we have the graph for the counterflow heat exchanger. So what we have here is the hot fluid and the cold fluid. They're gonna flow in opposite directions, and they're also not gonna enter at the same spot because of that. So in this case, we have the hot fluid is entering here, but then the cold fluid is entering over here. And then we have the same kind of idea for the outlet for each of the fluids as well. So if we look at this graph here, we see that the heat transfer between, in quotes, the hotter portions of the two fluids, they're going to be at one end, and the heat transfer between the colder portions of the fluids are at the other end. So for the hot end, that's over here on the left, and then for the colder end, that's going to be over here on the right. And then because of that, the difference in this temperature differential basically for the hot fluid and the cold fluid, it's not going to be as large at station 1 as compared to parallel flow. So if we look at this graph, we can see that we have this temperature differential right there. And if we go back up to parallel flow, we see that that differential is larger for parallel flow because we are starting at the inlet for both of those fluids where we have a really hot fluid and a really cold fluid. But for counterflow, we have the inlet for the hot fluid, but for that inlet, it's the outlet for the cold fluid. So because of that, we're at a high temperature for the hot fluid at the inlet, but the cold fluid, it's been heating up throughout this flow because it's going in the opposite direction of the hot fluid. So it's heating up to the outlet, which is at the same axial position as the inlet for the hot fluid. So I know, kind of wordy there, but you can see that relationship just right there. And then we have the same kind of idea for the outlet of the hot fluid and the inlet of the cold fluid. And then because of this, the outlet temperature of the cold fluid, it's now allowed to exceed the outlet temperature of the hot fluid. So this cold fluid here, that might heat up, continue to heat up, and it could theoretically heat up more than the outlet temperature for the hot fluid. Okay, so now that we got those kind of theoretical ideas out of the way, we're going to start and begin on the math portion of this, where we start to develop equations for the heat transfer in our system.
Remember me. Don't let your life pass you by, and weep not for the memories. Don't let your life pass you by, and weep.
Okay, so we're going to start this off by considering the case where we have axial variation of temperature in a tube with a uniform wall temperature, T sub W, with fluid flowing in the inside of the pipe. So fluid is going to enter at the inlet at x equals 0 with temperature T1, and it's going to exit at x equals L, the length of the pipe, at temperature T2. Okay, and then we're going to assume that we're heating the fluid, so we have the temperature of the wall is going to be greater than the local temperature of the fluid. So if we equate the heat transfer from the pipe wall to the fluid, we can have this equation. So we have Q dot times pi times the diameter for a differential length element dx is equal to, this is the fluid part, we have h, the convective heat transfer coefficient, times pi times the diameter multiplied by the temperature of the wall minus the local temperature times our differential length.
Keep not for the memories, as I will remember you. Will you
Okay, so this heat transfer that we have to the fluid, this is going to cause a change in enthalpy. So we're going to use this later on. So we have m dot Cp times our differential for the temperature. So m dot, that's going to be the mass flow rate of the fluid, and Cp, that's the specific heat for the fluid. Then we can rewrite the mass flow rate as m dot equals rho times v, the velocity, times our cross-sectional area. In this case, it's going to be for a circle because we have a pipe.
remember me?
Okay, so now what I've done is I've just rewritten what we had earlier for the change in enthalpy, and I plugged in our formula for the mass flow rate of the fluid. So now what we're going to do from conservation of energy, we're going to equate this change in enthalpy to the rate of change for the heat added to the fluid.
Don't let your life pass you by, and weep not for.
Okay, so like I said, from conservation of energy, the rate of change of enthalpy for the fluid is going to be equal to the rate of change of heat added to the fluid. So I've just equated these two, and what I had here is, I passed it, is just this part right here. That is the heat transfer that was from the wall to the fluid. So we're equating those two right there. Okay, so now what I've done is I've just made some substitutions here. So we already had this part on the left, we had that just above, right here. And then for the right hand side of the equation, what I've done is from earlier up here, we had this relationship for the heat transfer from the pipe wall and the heat transfer for the fluid, the convective heat transfer. Okay, so I've made those substitutions. And now what we're going to do is rearrange this, and we're going to be able to solve for the temperature distribution throughout the heat exchanger.
Don't let your life.
Okay, so I've just rearranged this, and now we're going to basically integrate this, and then we can start to develop that expression for the temperature distribution throughout the pipe.
Pass you by, and weep not for the memories. Don't let your life pass you by.
Okay, so what I've done now is I've just integrated those two equations at the top, carried out some boring math, and then we get to this final expression on the bottom, where we have the natural log of the temperature of the wall minus the local temperature divided by the temperature of the wall minus the inlet temperature is equal to minus 4hx divided by rho v d Cp. Okay, so now what we're going to do is we're going to take the exponential for these equations so we can get rid of that natural log.
And weep not for.
Okay, so we took the exponent, and then what I have here is I made just a substitution for beta, so I can make it just a bit more simple. And I've made a substitution within beta where I equated that to pi times the convective heat transfer coefficient multiplied by the diameter and then divided by the mass flow rate for the water times the specific heat. So for that, we already knew that the mass flow rate was equal to pi over 4 times the density times the velocity times the diameter squared. So I just made that substitution in there that we're going to use later on. Okay, so this is fine. However, we're going to now make another substitution where we typically want to find this temperature distribution for the inlet at station 1 and the outlet at station 2. Okay, so we're just going to plug in for that, and we're also going to utilize that substitution at the end there. Okay, so I've just gone ahead and I've plugged in T2 for the local temperature T, and then I've also put in L right there, so I plugged that in for X. Okay, so now we have this temperature distribution, and now we can use this to find the total heat transfer that we have in the pipe.
I will remember you. Will you?
Okay, so then I wrote out the equation that we have to find the total heat transfer in the pipe, which is given by big Q dot equals m dot Cp T1 minus T2. And then from equation star, right there, I've written out, or I've kind of rearranged that equation to solve for m dot Cp. So I just took the natural logarithm of both sides and I solved for m dot Cp. And then we can use those two equations there to solve for the total heat transfer in the pipe, which we now have as big Q dot equals h times pi dl T1 minus T2, and then the natural logarithm of T1 minus T wall divided by T2 minus T wall.
Remember me. Don't let your life pass you by, and weep not for the memories. Remember.
Okay, so equation new star, a different star than before. We're going to rewrite this for either parallel flow or counterflow in kind of a generic form. And we're going to have this in terms of the initial and final values for both the cold and the hot fluid. Okay, so we have the general form is just right there. It's pretty similar to equation star, but instead of the convective heat transfer coefficient, we're now going to have the overall heat transfer coefficient. And then delta T1 and delta T2, they're going to depend on whether the flow is parallel or counterflow. So you're going to use this equation here to solve for the total heat transfer, but you're going to kind of modify it with delta T1 and delta T2 depending on whether the flow is parallel or counterflow.
All the good times that we had, I let them slip away from us when things got bad. How clearly I first saw you.
Okay, so the values of delta T1 and delta T2, they're going to depend on the hot fluid at the inlet, so that's THI, the cold fluid at the inlet, so TCI, the hot fluid at the outlet, THO, and the cold fluid at the outlet, TCO. So we have, for parallel flow and for counterflow, we have delta T1 and delta T2. So you're going to plug that into that equation right there. So for parallel flow, we have delta T1 equals THI minus TCI, and for delta T2, that's going to be THO minus TCO. Let's go up, and we see that here. So we have, at the inlet, we have THI, and we have TCI, and then out the outlet, THO and TCO. So for parallel flow, we kind of stay consistent where we have I and I, comma I, at the inlet, and then we have O and O at the outlet. Okay, let's go down. Then for counterflow, we have delta T1, that's THI minus TCO, and delta T2 is THO minus TCI. So, again, these are kind of flip-flopped because we're in counterflow. So if we look at this, we have at the inlet or station 1, that's THI and then TCO, and then station 2, THO, the outlet for the hot temperature, and then TCI, the inlet for the cold temperature or the cold fluid. Okay, so now we're going to briefly talk about how to solve for the overall heat transfer coefficient, as that's one of the deliverables for the experiment. Okay, so I've taken our equation that we had earlier for the overall heat transfer and I've rewritten that to solve for the overall heat transfer coefficient U. So this is going to be different for whether you have a hot fluid or a cold fluid, but if you had a cold fluid, you can make the necessary change just right there. Okay, so in this case for the hot fluid, basically this is Q dot right there, where if we go up here, it's right here. So we just plugged that in. Okay, so we have that. So basically I just rearranged the equation to solve for this coefficient. And then you would of course need to make sure that you are using delta T1 and delta T2 correctly for whether it's parallel flow or for counterflow. Okay, so that should be it for this lab. If you have any questions on the theory or any of the equations or the theoretical concepts, just send me an email or we can talk through Zoom or Discord, whatever. So hopefully you guys enjoyed this last lecture. Sorry we can't actually do the lab in person, these last 3 labs. I think that's really important to do in person, but obviously given this case here with the coronavirus, that's not possible, and for a good reason. So anyways, I hope you have learned still at least some about these labs, and I'll try to get some videos up as well so you can get an idea of maybe what this lab would have looked like. So anyways, again, I hope you enjoyed this lecture, and then I'll have the data reduction up, as soon as I can. So thanks for watching, and I will see you in the next video.